Good morning. Welcome back to Krishna's classroom. We were looking at the concept of completeness of metric spaces. And we have even gave a characterization, discussed the details of that, and also to some interesting spaces, function spaces that we often come across, and we would like to explore, and which we have explored and shown that they are complete. So that's where we left in our last lecture. Now in this talk, we look at another interesting consequence of the completeness. We begin exploring what happens on the real line, which is our standard model for all sorts of results on metric spaces, and then possibly try to see how the same result would manifest in a general metric space. So we look at the so-called nested interval theorem. Let us first state the theorem. Let Jn be intervals on R in R such that Jn plus 1 is contained in Jn for every n belonging to then the statement of the theorem is that intersection over n is known. Further, that length of chain goes to 0 as n tends to infinity, intersection it's a beautiful theorem. So concept is something like this. So before we prove this theorem, let us try to understand it. Says on the real line you have got a closed bounded intervals a and b with the property that an plus 1 bn plus 1 is contained in a and b, may be properly So you have a sequence of intervals Jn. So each one of them is, so Jn is, we have defined as so so what happens is you have a nested collection of intervals. As you see, the further an plus 2, bn plus 2 is inside this and so on. Eventually, when you take the intersection, that means the set of all points which lie in every one of them is, then that set is non-empty. That's the first thing. The second statement says that the length of the interval, what is the length of the interval? The length of the interval is bn minus an. If bn minus an goes to 0 as n tends to infinity, then there is exactly one point inside that intersection. Okay, so let us prove this theorem. So we have an plus 1 contained in a and b for every n now this implies an plus 1 an and bn plus 1 an plus 1 is greater than or equal to an and bn plus 1 is less than or equal to b. Further, you also have for every okay. So in particular, in fact, for s greater than or equal to r, we have Js contained in J s minus 1 Jr. So the sequence shrinks Jr plus 1 and so on, and it just shrinks down to so you have got s greater than or equal to r, therefore this particular containment relation works, and that in turn implies that AR is less than or equal to AS and AS is less than or equal to BS and is less than or equal to BR. That implies AS is less than or equal to BR RS belonging to. So this inequality we have. Now we look at the sequence. Look at the sequence AN. Now the sequence AN is a sequence of real numbers which is monotonically increasing and is bounded above. So let E be the set of then E is a monotonically non-decreasing sequence of real numbers bounded above by so it's a bounded sequence. It's a bounded monotonically non-decreasing sequence. And from the monotonically increasing and bounded above by the least upper bound axiom. There exists a C belonging to R such that supremum. Now what we claim is that in fact what happens is it is the limit of the sequence. In fact C is equal to okay. Now we claim that C is in every one of these ANs. We observe that C is greater than or equal to AN And so also C is less than or equal to and C is the of E C is less than or equal to En for every n. What does this mean? This implies An for every. So we have proved one part of the theorem, okay, that this intersection is correct. Now you observe that it heavily depends on the structure of the real line. I mean, as far as our proof was concerned, many properties of the points on the real line were used. The properties related to what is called the monotonically increasing bounded sequence was made use of. You can give a likewise argument by taking Bn, and you know that the sequence Bn is bounded below by Am for any m, and again we can take the infimum of the sequence and make an argument. So there is no problem. Of course, in general the C and probably the limit of n tending to infinity Bn need not be the same. Okay. Now we use the assumption. Further assume length of Jn which is equal to Bn minus An goes to 0 infinity. Now we already have intersection over n known like this. Let in general there may be more than one point. We want to say that under the assumption that the length of Jn goes to 0, the limit is unique. Okay. So what you have is this. Suppose x and y are such that they are in the intersection of Jn. So you have this result, namely and let us assume x is less than y. So in general this is going to be the structure that you have. Okay. So which implies for every n. Okay. What does this mean? We have mod x minus y, which is the length of this, less than or equal to mod j. And we have our assumption. Now we are going to make use of the assumption, and this goes to 0 as infinity. What does it mean? It implies for every epsilon positive. Now we can give an argument using this. Now Ljn goes to 0 means that the length of Jn can be made arbitrarily small. So given epsilon positive, there exists an n such that Ljn is less than or equal to epsilon for, and that is true for every n, and therefore you see that given epsilon, mod x minus y is less than epsilon for every epsilon positive. What does this mean? So there is a unique limit for an, and the limit of an and the limit of bn, they become the same. Okay, in this case, in the special case that the length of these intervals go to 0. So that completes the proof here. So this is the nested interval. Now the natural question that you ask at this stage is this: we make a remark the non-emptiness of does not require the assumption does not require the assumption that limit n tending to infinity we are not using it at all except in the second part of the theorem. Now in such a case, you see, you have a unique, there is a singleton point that belongs to the intersection. Okay, so this is something worthwhile to know. Now let us see. So the question that we ask at this stage is this: in a general metric space, does an analog of this theorem. This is a question. How does this particular result gets possibly generalized in a metric space? Let us get back to our nested interval theorem. We have these assumptions. We have a collection of intervals Jn plus 1 for every n. This assumption. Then we are assuming we are rather proving economy. This is the main statement of the theorem. Okay. So note that Jn is the closed bounded interval An. Is a closed bounded interval. Now you see that if you drop this theorem won't be valid. Because for instance, suppose you were to take In A and Bn, open interval A and Bn, and you what will be the intersection of this? Can you make the same statement about this? For example, let okay, so let me not make this example, but that may be or may not be. Okay. So we have the assumption that Jn is a closed bounded interval. Now suppose we drop the condition that it is bounded. Okay. Okay, let us consider this. See, we drop this condition, closeness. Okay. Consider zero. Etc. Now you see that Jn plus 1 is an open interval. Jn. Okay. So Jn is open. Now you take intersection Jn. Take one to infinity. Now you see that limit n tending to infinity of 1 by n, this is equal to 0. And you can easily see that intersection is empty. 0 does not belong to that. Okay. 0 in fact does not belong to any one of them. But the limit of this is this. Okay. So you see that no other point, so any point alpha greater than 0 because you can always find, because there exists a number n such that alpha, and hence alpha does not belong to and which implies alpha does not belong to intersection J. Okay, but 0 is none of this. Therefore, the conclusion of the nested interval theorem does not hold. In general, we drop the condition that this is closed. Now let us take the boundedness. Okay. So let us take unbounded inverse. and may be closed. For instance, take when each Jn is closed but is unbounded. But not bounded. What about intersection Jn? And this you can easily prove that this is, once again, if you assume, so a number greater than n to be in it, then you can show that there exists a Jn which does not contain. It's the same type of argument that we use. So we observe that the assumptions like Jn is a closed bounded interval is significant in the validity of this theorem. Okay, that we make that observation. Now when we go to general metric space, you see, you have the concept of closeness. You could also have the concept of boundedness. So one of the immediate question that comes up is this. Metric space and an x with is closed and bounded. Possible to conclude it's not empty. This is the question that we observe that the form in the nested interval theory. In the nested interval theory, we have the sequence AN monotonic non-increasing, non-decreasing, and bounded. Hence, sequence and the limit exists. Because R is complete. This is important. So completeness of R plays a role, and it's not because the way in which we have argued these upper bound property we have, etc. So you have the completeness of R coming into play. Okay. So that is something that we have used here. And here, certainly, so in the general scenario, we have to assume X is a complete Now, once again, you are asking this. Now, we are willing to make all these assumptions that An is a closed, is a sequence of closed bounded subset of X. Okay. And the metric space X is complete. With these assumptions, is it possible to conclude that intersection An is the one? So the question is, the problem is this. So we now ask, remember when we work in a general metric space, we don't have, this is not structurally rich like the real line. There are a lot of things on the real line. Okay. So we assume X is a complete matrix. An is a sequence of closed bounded subsets X does this imply no. This is again something that we have to explore whether this would do. Now, if you try to mimic the proof of this, then the problem is possibly we can work out a a sequence of points, okay, and then try to get a limit of this. See, if we try to explore the same proof, what would happen? Take xn belonging to A. So you have an for every. Now you see that you have a sequence A xn. So we have a sequence xn. Okay. Now to get the limit of this, you know that the limit exists provided here the limit exists provided a Cauchy sequence. But none of the assumptions that we have made essentially helps us to conclude that this is a Cauchy sequence. Assumptions. To conclude, this is the problem. Okay. Because all that we have assumed is that An is bounded. Okay. Now let us explore an example. Let x be equal to a set of all natural numbers. Now let us assume what is the metric that we are going to use? We use discrete method. Okay. Let B metric on that is D of y equal to 1 whenever x is not equal to. Now then we have seen that bounded matrices. Therefore, every subset is bounded. Further, every subset of is closed and open. Okay. So any collection of subsets that you take, they are open. So suppose you take A and to B. So let's take a specific scenario. Etc. This collection. Now, then you see that each AN is closed and bound. Each AN is closed and bounded. And AN plus 1 containing A. What about the intersection? This you see is empty. So you see that obviously if you just assume the subsets AN are in a general matrix space, if you just assume subsets AN are closed and bounded, and it has the property that it's a nested collection of sets, you cannot conclude that their intersection is null. Okay? So you need something more to work on that. Here you see the difficulty that you encounter is that, oh, okay, is complete? Yes, it's a weird space actually. Okay? The only Cauchy sequences are constant sequences on, and they do converge on. Okay? Choose any other sequence. Only Cauchy sequences. Only sequences. Cauchy are the constant sequence. And they do converge. Other sequences, see, they are all bounded closed sequences, but the other sequences are not Cauchy sequences. Therefore, there is no limit. So you cannot push the arguments through. Okay? The completeness is not going to help you much in pushing the arguments through. So you see that the crux of the problem lies in proving that the sequence, you get a sequence, you can extract a sequence which is a Cauchy sequence, then you can use the completeness, and from the completeness you can conclude that the sequence converges to some element, and then expect that that particular element is going to be inside this. So how do we work a possible to get the sequences Cauchy? How do you work? Okay. So you see that one of the further assumptions that we can make is possibly for each of these sets you have what is called the maximum distance that you have in this set, because they are bounded subsets. Every subset is a bounded set. So there is what is called a maximum distance in any one of these ANs. Okay, and in this case you see that maximum distance that you can have is 1. Okay, and the problem is that this maximum distance never goes to 0, it remains 1. Okay, so that is where the problem is. So if we are to assume further that the diameter which gives the maximum distance in that set of AN goes to 0, then possibly we will get it. Okay? So we have tried to explore a proof of this. That doesn't help, right? So we shall further assume so if we further assume so this is the problem. It's the question of proving something is Cauchy. Okay. So we shall further assume that the diameter of AN goes to 0, infinity. That means the maximum distance in AN is what you call the diameter. You know that is bounded, so the supremum certainly exists. Okay, there is no problem. So the diameter is certain. Because the supremum fixes and it, because the space is bounded space. Okay. Now this leads to what is called the Cantor's intersection. So this Cantor's intersection. So let us make the statement of the theorem. Okay. I think I'll take it up in my next lecture. It's already an hour, more than an hour. Okay, so thank you very much. So this is the sort of curtain raiser for the Cantor's intersection. How possible your nested interval theorem would have a generalization in a general metric space. Okay, thank you very much.